Stoichiometry is a lot of what people define as chemistry. Almost all of Chem 2, whether we took honors or regular or took it at another school, is focused on calculations related to the moles and reactions, putting those things together. The word stoichiometry we see has to do with elements and measuring them. It's based upon the law of conservation of mass, or the idea that whatever I start with, I end with the same amount. No matter what skills we add on after this, it comes back to reactions and it comes back to understanding moles and stoichiometry. So even as we get into new things or more challenging things, equilibrium, kinetics, and thermo, we're still building our basics of stoichiometry. And stoichiometry is all about putting together what we know about the mole, atoms, molar masses, and molar volumes with the application to a chemical reaction. When we have a chemical reaction, those coefficients do tell us how many atoms of each reactant react with the atoms of the other, but that can also be scaled up to the numbers that we can actually see, the billions upon trillions of atoms that we would call moles of atoms. So those coefficients, for practical purposes, really are more telling us how many moles of one thing react with another. They don't tell us how many grams of one thing react with another. And that was a big part of chemistry becoming an actual science as we were getting into both the industrial and scientific revolution, defining elements, defining compounds, and understanding how they react in terms of mass and moles and how those are different. When we are doing stoichiometry, what we're doing is thinking about, well, what have we measured? How does it relate to the number of moles? And how can I connect that to something else? All of the math comes down to the central idea that's down here. So up above, I've got some color-coded things. But if I wanted to know the moles of a substance, I'm not able to measure that directly. But I might be able to measure the volume, even if I'm not at STP. I might be able to measure the mass. I might be able to measure the volume, even if it's an aqueous solution. I might be able to measure the volume at STP, or I might be told or be given data that allows me to know how many molecules there are. With any of those 5 different things, there is a value or an equation that lets me know how many moles that is. So when I am given one of those things, I would want to know how many moles of that substance is there. If I am then asked about another chemical that is a reactant or a product that I am trying to make from that, or the reactant that made that product, I would look at the coefficients, which is the mole ratio. We'll see here there are some other things that can directly be connected with the mole ratio, but almost always, no matter what we have, we change it to moles. Then we go to the mole ratio, which is just the coefficients. That mole ratio tells me the moles of the other thing, and I can use that to end at moles or find any of the others. Up above, remembering that no matter what we have, we change it to moles. If I have mass, particles, or volume at STP, there is a number that I can either multiply or divide by to get that to moles. That number is either Avogadro's number, the molar volume, or a number that we find on the periodic table. We practiced all of those in previous problems. If I had an aqueous solution, something dissolved in water, I do not have a specific value, but I do know or can think about, as we'll talk about shortly, its concentration or molarity. And there is an equation that allows me to connect molarity, moles, and volume in liters and solve for any unknown. If I know the molarity and volume, I can find the moles. If I know the moles and volume, I can find the molarity. If I know the molarity and the moles, I can find the volume. Lots of flexibility. And similarly, I can do something with a gas not at STP. At STP, it's easy, it's 22.4. But as I raise the temperature or raise or lower the pressure, that volume changes. And this equation with constants and values given on the periodic table can be used. A lot of Chem 1 was focused on this. So that was the repetition we tried to do. build these skills, see the same things over and over, see them in different forms, start at point A, get to point B with all of these skills. When we were doing that, there were some key terms. Whenever we do a calculation, we call our answer based upon that calculation our theoretical yield. Sometimes it's just called our answer. Sometimes we just think about it as our yield or how many grams. But technically, that's theoretical because it's only based upon the numbers. If we went and took those exact same amounts of chemicals and took them into the lab and measured it, we would be able to figure out how much could we actually make. More often than not, we're going to make a little bit less than actual, and we might want to know how much less by using an equation to find the percent yield. In reality, our actual yield would have to be less than or equal to our theoretical yield, but sometimes if we collect an incorrect product, if our product is still wet, if our product is not pure, our actual yield can be weighed as a higher number or recorded as a higher volume than what our theoretical yield would account for. We can then, whether it's above or below 100, kind of think about what might have went wrong in our reaction process to give us a yield that is too high or too low. And as we're doing this, we have reactants that turn into products. When we start off, we often think about the exact amount of each thing that we need, just like if we were doing a recipe and collecting all of our ingredients. But if we were going to make cookies, we might get out our 2 eggs, our 2 sticks of butter, but it's very rare that in our cupboard we have the exact 2 1/4 cups of flour that we need. We probably have a big bag or big container, so we're going to have some flour left over when we're done. We might even have some eggs or some butter left in the fridge when we're done. The thing that we have just barely enough of, maybe we only have those 2 eggs left, that's going to determine how many batches of cookies we make. In chemistry, the chemical that we have that determines how much stuff or product we can make is our limiting reactant, or the term reagent is a synonym for reactant. It's the thing that completely gets used up. None of it's left over. You can't open up the cupboard and find any more of it in terms of eggs or butter. And it's not necessarily the thing that we have the least of. It's the thing that we use totally up. It's not just the thing with the smallest amount. And we'll do our calculations down here because it has to be proven with calculations. But once we know what ran out, we can figure out, did I have something else left over? If there was something that was left over, if it didn't react in that perfect 1-to-1 ratio, and the perfect example of this is right up here. In this example, I had the exact amounts of methane and oxygen to make products, but here I ran out of oxygen before I ran out of methane. Oxygen, even though there's more of it, was the limiting reactant, and methane, even though there was less of it initially, I didn't need as much, so it was the excess. So I can figure out what is limiting and what is excess by calculations, or sometimes even looking at a diagram, but then I can also calculate or know how much is left over. Kind of refreshing ourselves and flexing our stoichiometry muscles and getting those back in shape is the most important skill that we're going to do throughout this unit. So how can we convert 2 moles from all of our different units? Remembering to carefully show our mole to mole work. And then what are we trying to end at and how can we get there?